Welcome to ashatech.com, your engineering sciences channel. In this video, we are looking at the design of machine elements, and in this particular video, we are looking at shaft design. A horizontal nickel steel shaft rests on two bearings, A at the left and B at the right end, and carries two gears C and D located at distances of 250 mm and 400 mm respectively from the center line of the left and right bearings. So we are given, this is from here to there, we have 250 millimeters, then we have 400 millimeters. From the center line of this bearing, the center line of this gear D, we have 400 millimeters, and from the center line of C to the bearing A, we have 250 millimeters. The pitch diameter of gear C is 600 millimeters, and that of gear D is 200 millimeters. The distance between the center line of the bearings is 2,400 millimeters, and the shaft transmits 20 kilowatts of power at 120 revolutions per minute. The power is delivered to the shaft at gear C and is taken out at gear D in such a manner that the tooth pressure FTC, that is the tangential component of the normal force that exists between the two gear teeth, then the tooth pressure FTC of the gear D and the FTD of the gear D act vertically downwards. Find the diameter of the shaft if the working stress is 100 megapascals in tension and 56 megapascals in shear. The gears C and D weigh 950 and 350 newtons respectively. The combined shock and fatigue factors for bending and torsion may be taken as 1.5 and 1.2. These are just the factors of safety, of course taking account of one when we design against bending and when we design against torsion. We will use two stress theories. One is the maximum principal stress theory, and that is which is telling us in tension. Then the 56 megapascals in shear, we will use the maximum shear stress theory or Tresca's theory, that at the end of the day we have two diameters, and the maximum diameter is the one that we will take, that will be able to withstand failure against shear and the failure against bending. Okay, so this is the diagram of the scenario that is given to us. This is the shaft. These are gears supported on this shaft by a key, and these are bearings A and B. Then the distance is given between A and C. C and D and B are also indicated. Then between C and D is also indicated. Between A and B is also indicated. Let's look at the solution to this problem. When I look at the shaft, this is the shaft. I look at it from the side of gear D. I will see two circles, three circles actually. One to show the cross-sectional area of the shaft. Then I will see the smaller circle and a bigger circle to represent gear C. Then the tangential forces or the tooth pressures are acting vertically downwards, and that one of C is FTC, that one of D is FTD. Then the data provided to us, this is the information provided to us. We have power that we have converted it to watts, that is 20 times 10 to the power 3. Then we have the fatigue and shock factors in bending and in torsion. Then we have the radius of, we are given that the diameter of gear D is is 0.2 meters, and therefore the radius will be 0.1 meters. Then the diameter of gear C is 0.6 or 600 millimeters, and the radius would give you 0.3. Of course, you divide this by 2. Then the speed in revolutions per minute is 120 rpm. Then the weight of gear C is 950 newtons. The weight of gear D is 350 newtons. Then the stress in bending is 100 megapascals, that is times 10 to the power 6 newton, of course Newton square meters. Then tau, which is the shear stress, of course the stress in torsion is 56 times 10 to the power 6 newton per square meters. Okay, so when I look at this particular problem, this is how I have it. I have FTC and I have FTD. The distances should be provided. This is 1.7 meters from there to there. Then this is 0.4 meters. This is 0.25 meters. Okay. Now, torque transmitted. Let us look at torque or power transmitted. So torque is obtained from power equal to torque times the omega, whereby omega is the angular velocity or angular speed, but angular speed is equal to 2 pi n divided by 60. So if I substitute it in the power equation, then the power will equal to 2 pi n t, which is torque, divided by 60. What does it give me? It gives me torque as 60 times power divided by 2 pi n, and these quantities are provided to us. Power is 20 times 10 to the power 3, then n is 120, and this gives me 1591.59 Newton meter. That is the torque, and this is the same torque that is transmitted by both gears, because it is given to the shaft at C and then taken out at D, so it is the same torque that is going to be transmitted. So meaning that TC, the torque at C, or the torque transmitted by gear C, is the same as the torque transmitted by gear D, and is equal to 1591.55 Newton meter. Okay, let us look at gear C. The gear C, if we look at its equilibrium, we are saying the tangential force, the force that is responsible for torque transmission, is the tangential force that is a component of the normal force. Remember, there is always a tangential force. Then you also have a force in the radial direction, so it is called a radial force. Then of course this is always giving rise to a force Fn, which is the normal force at the gear tip. So the one responsible for torque transmission is the tangential component. Now that means we can define a torque for gear C as Tc equal to Ftc times Rc. So Ftc will therefore equal Tc divided by Rc, and remember Rc, we have it, we have already Rc, we have it as the radius, which is 0.3. Then we know Tc as 1591.55. we can bring it in here, and we will have 5305.1. we can take 17 newtons. This is Ft. Okay, we move. Total vertical load, therefore, on the shaft at point C, or at gear C, we will see that the vertical load will involve the tangential component of the normal force transmitted at the gear. Then we also have the weight of the gear at C. So the weight of the gear is Wc, and the tangential component of the normal force is Ftc. So if we substitute it in here, we will have 5305.17 plus 950, which is the weight of gear C, and this gives us 6255.17 newtons. We go and consider the equilibrium gear D. Also, gear D has a component of the normal force called the tangential that is responsible for torque transmission and is called FTD. So if we can also define the torque for gear D, which will be FTD times RD, because we know torque is a turning moment, and therefore it is always equal to the product of force times the perpendicular distance from the turning point from the action of the force. So the force involved is FTD, and the radius or the perpendicular distance from the turning point to the line of action of FTD is RD, which is the radius of gear D. We have all this information, and this is going to be FTD divided by 0.1, which is the radius of gear D, and at the end we have 15915.5 newtons. So we need to also determine the total vertical load on shaft at D, which will equal to the sum of the tangential force plus the weight of the gear D. The weight of gear D is provided as 350 newtons, and the FTD, the tangential component, which is also pointing vertically downwards, we have calculated it from above as 1591.5. Then 15915.5 plus 350, this gives us 16265.5 newtons. Now if we assume the shaft as a simple supported beam, if it is assumed to be a simple supported beam, and we consider those vertical forces that are provided to us, or the ones that we have just calculated, we will experience a reaction at bearing A, which is RA, and we also experience a reaction at bearing B, which is RB. If we assume, of course, these forces have been given to us, they are vertical, they are pointing vertically downward. Of course, even if we made them point upwards, still the reaction would face downward. So it is still the same scenario, but in our case we are considering it to be like a simple supported beam that has point loads that are facing vertically downwards. So our task, our challenge is to find RA, the reaction at A, and the reaction at B. So apply equilibrium conditions to this simple supported beam or shaft. Then we have to sum upward forces to equal to downward forces, and the RA plus RB is therefore equal to 0.67 newtons. Okay, we can call maybe this equation 1. Then we also look at the sum of moments about A. With sum moments about A, we will have clockwise moments, which will be VC times its perpendicular distance from A, and VD times its perpendicular distance from A. Then we will also have RA in an anti-clockwise direction, so we will have an anti-clockwise moment due to RB. So RB times the distance from the line of action of RB to A, that will be 2.4. It will equal to 6255.17, which is VC times 0.25, then plus 16265.5, which is the reaction, which is the vertical load at D times its perpendicular distance. This will be 0.25 plus 1.75, and that will be 2. So if I solve that, I will get RB as 14206.16 newtons. Okay, then if we use the equation 1, we will be able to determine RA. So this RA will equal to 8314.5 newtons. That is, if I just go to this minus this, I will get RA. So let us determine the maximum bending moment. We need to determine the maximum bending moment, because at the end of the day we need to use the maximum principal stress theory and be able to determine the diameter of the shaft. Then we later on use the twisting, the twisting moment, the maximum twisting moment in the Trescal theory, which is the maximum shear stress theory, and be able to determine the diameter of the shaft. Then here we are saying maximum bending moment at A. We know at supports for a beam, as usual, at supports there is no bending moment here and there. So the bending moment MA, MB are equal to 0. Then we also determine the bending moment at C. The bending moment at C, we can see that if I hold here, for example, then I consider this moment due to RA. That is the moment that I will experience. Likewise, if I hold here and use this side, I will have a moment due to VD and RB. So since I have lots of forces this way, I can simply use this RA. After all, it will be the same moment. So moment at C will equal to RA times the perpendicular distance from C. So that will be 8314.51 times 0.25, and this gives us 2078.63 newtons. Then, of course, Newton meter. This is the bending moment, which is the product of force and distance. Then the bending moment at D, I also go to D and hold here. The moment I will experience here will be due to RB. Yes, I can use this side because I have lots of forces. To avoid that tedious work, I will simply use RB. So since it is the same moment, so it will be RB times 0.4, and that will be the moment, the bending moment I will experience at D. So the bending moment I will experience at D will be 14206.16 times 0.4, and this is equal to 5682.464 Newton meter. Okay, then the bending moment, therefore, at D is the maximum bending moment. Yes, the maximum bending moment. I'm going to compare the four. Here they are 0, then I look at this, I look at this. So the maximum or the biggest value is 5682.46. So 5682.46 Newton meter is going to be the maximum bending moment. Let us also compute the equivalent twisting moment. The equivalent twisting moment, of course, we want to use it in Tresca's theory to determine the diameter of the shaft. So this equivalent twisting moment is equal to, remember, there is a, why are we calling it the equivalent twisting moment? We have an action of two things: a torque, which is a twisting moment, and a bending moment. So for us to determine the twisting moment to use, we will actually find out the equivalent twisting moment. So the equivalent twisting moment, TE, is equal to square root of KBM, everything squared, plus KT, T, everything squared, and all this is under a root. This is the shock and fatigue factor in bending. KT is the shock and fatigue factor in twisting, or when we apply torque, that is when there is shearing of the component. So these factors are provided to us, so I will just substitute in 1.5 times 5682.46 everything squared, plus 1.2 times 15, 91.55 everything squared. I'll have that equivalent twisting moment as 8735.04 Newton meter. What about the equivalent twisting moment? That according to Tresca's theory, the equivalent twisting moment also is equal to pi out of 16 times tau, which is the shear stress, the allowable shear stress or the working shear stress, times the tube of D, which is the diameter. So the two, this one and this one, are equal. So what I do, I just equate the two so that I have pi out of 16 times tau times D to power 3 is equal to 8735.04, and the diameter D is going to be the tube root of 8735.04 times 16 divided by pi times tau. Tau is 56 times 10 to power 6. So I take the tube root of that, and I'll have 0.0926 meters, and the diameter of the shaft, according to shear stress theory, or the Tresca theory is going to be this times 1000, and this will be 92.6 millimeters. What if I apply the maximum principal stress theory? I know the equivalent bending moment has to be calculated, and the equivalent bending moment according to the maximum principal stress theory is ME equal to a half into KBM, whereby this is a fatigue factor in bending, then this is the maximum bending moment experienced in the shaft, plus the square root of KBM squared plus KT T squared, and everything under root. Then ME will therefore equal to, I substitute in these values, then at the end I will have the equivalent bending moment as 8629.37 Newton meter. But the same equivalent bending moment is equal to pi out of 32 times sigma d cubed, and if I get this, I equate it to this, then my d will equal to the cube root of 32 times 8629.37 divided by pi times 100, because 100 is the maximum stress in tension, times 10 power 6 if I convert it to pascals. Then I will have d equivalent to 0.09579 meters. If I multiply it by 1000 to convert it to millimeters, then d is equal to 95.79 millimeters. So I look at the two values. I have a diameter of 92.6 millimeters and a diameter of 95.79 millimeters. So I take a maximum. So diameter D is able to withstand both stress theories. It will withstand the failure in shear and the failure in tension. So it will be 95.79 millimeters. So I just go to the table and look for the standard value that is close to this, and maybe it can be D equal to 100. So I take 100 millimeters diameter and use it in my design. Thank you so much. See you in the next video.